Okay, good afternoon, everyone. I would like to start. Thank you for joining us. Thank all of you for joining us today. It's great to see very familiar faces and people that have been actually involved in the project in previous stages of the project. So I would like to start by acknowledging the support from a lot of people from Curtin University, particularly the Curtin Corrosion Center, and the School of Biomedical Sciences, the Curtin Oil and Gas Innovation Center, who actually provided the scholarship for Lina to execute a lot of the experiments and research work that would be presented today. And of course, the Western Australia Museum that has also given us permission and to publish and to show some of the photographies that we will show today. A special thanks to people like Professor Elizabeth Watkin from Biomedical Sciences, who have been working with us for a long time on this project. Ian McLeod, Professor Brian Kinsella, who are the real corrosion experts, and they have been provided scientific contributions to our work and peer reviewing our scientific publications. So thank you for that. And of course to Andrew Woods, who was our technical lead for the 2015 expedition, and he's been very supportive throughout all these years. So this project initiated a few years ago when I was given the opportunity, the great opportunity to join the Sydney Kormoran project that was part of the 2015 expedition. To revisit the wrecks of the HMAS Sydney 2 and the HSK Kormoran. My role was basically to develop research opportunities with rusticle samples that we were potentially going to collect during this expedition. And by rusticles, I'm referring to this iron-oxide formations that you see on the surface of the wrecks. You can see rivers of rust, to say it that way, but we have seen them as, structures hanging from the surface, similar to stalactites that you probably know. And we know they are formed as a result of corrosion in deep ocean waters. And Lina will be talking more about that later on. Now, for those of you that don't know much about the history behind this project, I will just be very brief with this. The HMAS Sydney 2 is Australia's most famous warship. HMAS Sydney and her crew were the pride of the Royal Australian Navy. And on 19 November 1941, during the World War II, HMAS Sydney 2 and the German raider HSK Kormoran encountered each other off the Western Australian coast. And following a sea battle, both ships were destroyed, which resulted in the sinking of the two vessels. So on that day, all Sydney's 645 crew members perished. The HSK Kormoran itself lost more than 80 sailors. There were 318 Kormoran survivors who later were the ones providing eyewitness accounts of the battle. On that day, both ships were lost, and they disappeared without a trace left. This has been considered Australia's greatest naval tragedy, and it is a very significant part of Australia's history. So if you are really interested about all this history and learn more about this, I really recommend you to have a look at the books. Especially this one was produced by the Western Australia Museum after our 2015 expedition. It's called From Great Depths. And also, there are a few places that I recommend you to visit. So last week I happened to be at Shark Bay, and I was very fortunate to have some time to visit the Museum of Geraldton. For the first time, I could watch the documentary, which is really nice, a 3D experience. And this was followed by a visit to the HMAS Sydney Memorial at Geraldton. It was a very emotional time for me, and also to reflect on this project and the real life real-time, real-life impact of this strategy, and to connect to those stories of those that were part of the Sydney crew and their families, and to remember those men that lost their lives in the service of the country. So you can understand that it can be difficult for me and for the team sometimes when we get all excited about the science that we're doing in relation to this project, because of obviously the tragedy that is behind this. But it's good somehow to feel that somehow through our work we can also help share the memory of those men. And as we mark the 80th anniversary of the battle between the Sydney and Kormoran this year, I strongly recommend you to visit Geraldton. And there will be quite a number of events going on there, and some special displays and exhibits if you want to visit Charbake. So going back to the story, the exact locations of the vessels remain a mystery for nearly 67 years, until the Funding Sydney Foundation, with support from the Australian government, engaged an international team that located the wrecks of both vessels in 2008. The wrecks of HMAS Sydney 2 and HSK Kormoran and associated debris fields were lined 22 kilometers apart, 290 kilometers from the WA coastline of Shark Bay, as I said before, at a depth of 2,500 meters of water. As I said, that was in 2008, and then in 2015, there was this expedition that was very meticulously planned to revisit the wreck sites. This was done by a team by the Western Australian Museum, Curtin University, and the expedition crew revisited the wrecks on board a Dove subsea vessel, a Scandi Protector. The expedition aimed mainly at surveying and re-imaging the wrecks in a much more comprehensive way and detail that was not possible before. So the idea was to digitally preserve the two wrecks, and in that way give permanent access to the community and the public to these inaccessible heritage locations. However, this time it was proposed to include a science program to add value to the project, and that included actually taking samples and be able to answer some very interesting questions about the role and fate of the wrecks in the deep sea ecosystem. But the challenge was always that the wreck sites were or are cultural heritage places, so the original permits excluded any physical contact and sampling. So there was the need to engage with several stakeholders, including communities, Sydney Kormoran families, that were consulted to reach some consensus about how we were going to approach this issue of, taking some samples. The eventual decision was that no physical contact would be made with the main hull, and therefore we were only allowed to take samples from the bow section. And you will see later some really beautiful videos where you can see the bow of the Sydney and see that it actually lies nearly 500 meters away from the main hull. And in the case of the Kormoran, we actually sampled from the engine block, which is lying about 1 kilometer from the large piece of the main hull. So being able to include this sampling in the science program was really a once-in-a-lifetime opportunity for us. Not only are the wreck sites difficult and expensive to access, so just to let you know, the cost of the expedition was around 2.4 million, but the samples are literally unique and contain really valuable information from processes occurring at great depths in the sea. In particular, the corrosion mechanisms and rates in deep waters, which remains an area that is of limited knowledge for us, because we cannot extrapolate from the shallow water investigations that are typically available in the public domain. Also, based on our links with industry, we envisage that this work will provide opportunities in the area of decommissioning, which is a big area now in Australia, and will help us with some predictions of what will happen with subsea oil and gas infrastructure in deep Australian waters once they complete their service life. Okay, so these were the type of samples that were collected during this 2015 expedition. So we collected the rusticles from the surface, water, and some core sediments. And they were all conducted following strict sampling protocols that we provided. Some of the sediments, some of the scientists wanted to study hydrocarbon degradation in the deep sea. And you can see here the rusticle. This is the rusticle scraper that was designed for the collection of the rusticles. This is the for the collection of the core sediments. And here are some of the pieces of the rusticles that we preserve at the Curtin Corrosion Center. So as I said, very strict protocols for everything. Some of the rusticles as well, revealing the real color of the rusticles. Now, rusticles have been observed on several iron hull shipwrecks worldwide. They became very famous through the underwater photographs of the HMAS Titanic in the North Atlantic Ocean. They had already been described as highly mineralized structures, mainly composed of iron oxides and hydroxides, but also a very complex community of microorganisms. So we were very interested in preserving not just these iron oxide formations, because obviously we wanted to evaluate the morphology, composition, properties, and see how close or how similar were compared to the other ones that have been described in other geographical locations and at different water depths. But we were also very interested in preservation of the genetic material to characterize those microbes that were part of the rusticles, and also be able to recover living microbes from those samples for cultivation, isolation, and characterization. So those microbes we actually have in our laboratory now. These were our research questions. So what are the rusticle properties and composition? And then you can see here some of the, so you've been seeing before also scanning electron microscopy images, high resolution of the rusticle samples. Other question was how do they form and grow and at what rate? What biotic and abiotic, so just chemical processes that are involved in their development? And what is the link between rusticles growth and preservation or decay of the underlying structure? So far, we have been able to publish 2 research articles in materials and corrosion journals. We have the first one was this one you can see here on the left side. That was the first paper, and it was basically a systematic analysis of the rusticles using X-ray microcomputer tomography, along with surface and chemical characterization. So we reported basically morphological structure, properties of the corrosion products. And interestingly, we found significant differences, as you can see here, the 3D structures and some of the key components inside the rusticles and how were they distributed. And we found, interestingly, significant differences between the 2 shipwrecks, so from rusticles from the Kormoran and the Sydney. And again, Lina will talk about that more in detail. And our second publication was something that was published this year. It was featured in Materials and Corrosion. After the publication, it was well received, and it was also invited as invited speaker for Chemobionics annual meeting this year, which Lina presented, and we got really excellent feedback. So with this, I just finished the introduction, and I just hand it over to Lina, who will present the details of this particular piece of research that I just mentioned. Yep. Okay. The microphone.
So hello everyone, I'm Lina. Thank you for coming. Laura, you're right back. Yeah, thank you for coming. I'm going to talk to you about my research. Here you can see that it was featured in the cover page of the Materials and Corrosion Journal. So the title of my research is Deep-Sea Corrosion Rusticles from Iron-Hulled Shipwrecks. The paper is in collaboration with Professor Elizabeth Watkin and Associate Professor Laura Machuca. So what are rusticles? Are vertical tube-shaped iron-oxide accumulations, and as Laura was mentioning, they are usually found in deep sea environments. The most famous ones are the ones in the Titanic, and was the first ones that were described. Just to keep in mind that 74% of the ocean's depth lies between 3 and 6 kilometers deep. The Titanic is currently at 3.8 kilometers depth. So you can see these vertical hanging rust structures like stalactites, as Laura was mentioning, over the rail and the hull of the ship. Other deep sea shipwrecks, for example, the Titanic that is in the North Atlantic. There are other shipwrecks that have been described in the Gulf of Mexico that also present rusticles. And these ones, the ones that from the HMAS Sydney and the Kormoran, are the first one described and characterized for the Indian Ocean. They don't happen just on shipwrecks. They can also happen in industrial components or parts like this mooring chain. For example, here these ones are on the left in the Gulf of Mexico at around 1,800 meters, and the other ones in the coast of Africa that are also around 1,000 meters. For example, this one on the left in the Gulf of Mexico was around 5 years in service when they started developing rusticles, and this other one you can see that it developed a really big rusticle. And you can also see a little, well, not little, it's a really big shrimp here. So what happens with these mooring chains is that if they lose 2% of the diameter, they have to be replaced. And this just takes a lot of logistics and economic efforts to replace these chains. And it can also happen if we want to decommission certain structures. We will see what happens when with the lower part of the structure, or the structure that was underwater, and a difference between the above water part of the structure. So this is the first diagram of the rusticles from the Titanic. As you can see, they have a very organic nature. They like flow out of the metal parts. They have these channels, they have ducts. They look like really organic and like plant-like. And you can see all these other fibrillar structures and cavities. They look like a lung also inside. So they are currently cylindrical. They have a central cavity that usually has a lower pH. They are formed of oxide layers of goethite mostly and lepidocrosite. The second most abundant component is silicon, and the composition can be influenced by the paint of the structure, the metal of the structure, or the cargo they held. For example, there was one that was carrying a bauxite cargo, and the rusticles were mostly aluminum, and they were a different color. They were white. This was also like SEM images from the Titanic, and you can see that they seem like bacteria. They also seem very organic. So all these observations cemented the idea that rusticles were formed by microbiologically influenced corrosion of the steel of the shipwreck. So we're basically bacteria eating the steel in the shipwrecks. But is it? So that is where I come into the picture and propose another possible mechanism of them being formed over this over the shipwrecks, and why they're mostly found in deep water. So the influence of deep sea chemistry and how the rusticles increase in abundance with depth. For example, here in this study in the Gulf of Mexico, several shipwrecks, and as the deeper they go, the greatest density of rusticles formation, with the Alcoa Puritan having the greatest density. And you can also see that the concentration of these phosphates, silicates, and nitrates in this deep sea, as the Alcoa Puritan is, increases in concentration, mostly more than 10, 20 times. So there's an influence of deep sea chemistry that is favoring the formation of these rusticles. The solubility of carbonate also increases with depth, but what they were looking on previous studies, what the corrosion source of iron is necessary for their steady growth, but at that time there was no plausible sustainable cathodic reaction for rustical formation that has been identified to take into account the dissolution of this metal from the hulls. So that is what we are trying to find out. So there's another influence of hydrostatic pressure that has a direct impact on the corrosion products and the corrosion process. They can change the corrosion products composition, morphology, and consistency, increases the water absorption into the coatings, and enhances localized corrosion and pit formation on several metals and alloys. So that is what I am taking into account into formulating a new rustical formation hypothesis. Now, specifically to our site, like the shipwreck sites, here you can see this paper took samples, deep sea water samples from this region really close to the Sydney and Kormoran. And you can see that, for example, silicate increases more than 10 times in deep sea. Sadly, they didn't sample below 1,000 meters, well below 800 meters, but there's a clear profile in all the samples where silicate increases several times with depth. The other site conditions, the temperature, really cold, really low amount of dissolved oxygen, really high pressure, remember it's 2,500 meters. The salinity that stays almost constant through the ocean, pH 7.6 that is affected by the increased solubility of carbonate with depth, and a total organic carbon of 3 milligrams per liter. That is really low compared to the surface waters. So now time for 3D images. So yeah, my first, my initial process of studying these rusticles was to obviously take a look at the footage Andrew and the team gathered from the rusticles. It was hours and hours of footage. So I found that, for example, when these, you see a number there? So I was trying to find patterns in both shipwrecks. So I started observing all the holes, the different parts, the guns, and they were basically growing everywhere. So yeah, you can see the different parts, like life-saving boats and Carly boats and guns. I think there are some parts. And it feels so lifelike that I just want to do like Matrix when this comes. Yeah. I feel like I'm going to be chopped over. So yeah, I started observing the different, for example, morphologies of the rusticles. You can see, for example, here some rusticles are open-ended and are like cylindrical. The other ones are closed-ended and are like conicals. How they flow sometimes from the hull. Sometimes they are like point-like. They just grow from a single point on the hull. So yeah, you can see anemones also growing, so we don't get dizzy. This portion of the hull, you can see the anchor here. And if we go to the other side,
Sydney.
yes, the HMAS Sydney, yes, the bow. You can see the depth measurements or the waterline measurements here on the hull. So if we can zoom out a little bit, what do you notice here? The ship is upside down. So this is the above water portion of the ship, and that is the underwater portion of the hull. So you can see that the underwater portion of the hull is a preferential rustical site. So we were wondering, why is it happening? Why this above water portion of the hull has been the same amount of time and no rusticles are appearing here? Well, not as abundant as the underwater portion of the hull. And this happens in both shipwrecks. The Kormoran is upright. So we were also considering, because I observed the Kormoran first, so I was considering like an influence of the sediment, but then I see this other one that it was upside down, and the same portion of the hull was presenting all these rusticles, and it was the same portion that the Kormoran also was presenting all the rusticles. So we were wondering, why is this happening? We found an explanation that I'm going to tell you about in a moment for the underwater portion of the hull, but this above water portion remains a mystery why it's so intact. So yeah, you can spin around a little bit more. Yes.
So the Sydney was hit by a torpedo from the Kormoran, and we can see the torpedo damage. Okay. We can see the torpedo damage just in this section here. We'll just look a bit further back. And that eventually led to the bow section detaching from the main hull of Sydney. The main hull of Sydney is around, I think, 200 or 300 metres away from where this is located. So it broke off and landed in a separate location. But as Lina mentioned, there's lots of rusticles along here where there's like an edge for them to form. There are some anemone on Sydney, but there's actually many more on Kormoran. So over here is a 3D model of a section of Kormoran. This is about 20 kilometres away, so it's not right side by side as we've got indicated here. This is just for illustrative purposes. Yeah, on the Kormoran site there are many, many more anemone. And here's one in the background, which we believe to be about 30 to 40 centimetres in diameter. Now this we believe is part of the bridge structure of Kormoran. Kormoran's a very different wreck site. Kormoran was carrying around 300 sea mines, and the crew set a time charge on Kormoran before they abandoned ship, and eventually the ship erupted into a huge explosion. So about 45% of the ship remains in one piece, and the rest of it is ripped up shreds of ship pieces, big and small, and amongst this portion is one of the unexploded sea mines. So you can see it's encountered a bit of damage, which could be a combination of both the blast itself, but also the fact it's sitting at 2,500 metres underwater. Now this 3D model and the other ones we've been looking at have been reconstructed from the over 500,000 photographs that we collected during the expedition in 2015. And these are just some of the initial results that we generated. This model here has been generated from probably about 3,000 photographs. And you can see the level of detail in here is really, really good. But we're currently working on techniques to reconstruct the entire wreck of both Sydney and Kormoran and significant parts of the debris field. And we're doing that using the Aussie Supercomputing Centre to provide some high levels of raw computing power. So with that, I'll pass you back to Lina, and you can take your 3D glasses off.
So continuing with the analysis of the footage, these two images were published on the book. One for the in the book, one for the 2008 expedition, and the other one from 2015. So you can see the same part of the shipwreck, but 7 years apart. I, after a lot of research, found the measurements of these little portholes. Well, not so little, 15 centimeters in diameter. So the rusticle in this image has grown to about half of it. So it's about 7 centimeters in 7 years, which gives us a growth rate for the rusticles of about 1 centimeter per year. More footage analysis, you can see the rusticles here hanging, and once they reach certain length or weight, they fall off, and the conditions in deep sea are so calm that they just float down, well, descend very calmly into the sediment, and you can see intact rusticles lying here, and I call these like a cemetery of rusticles, and then they become part, as you can see, part of the sediment. And then again to the cycle of the elements. Another little torture that I experienced was during this footage. Each time the ROV came close to these rusticles, the thrusters made them just puff into a cloud of rust. And I died a little inside. You can also see here open-ended rusticles with a close-ended little tip. Also, when the ROV was sampling them with the little scoop, they also fell into a cloud of rust, and we could only recover small pieces of the rusticles. But this image was really, really informative, because you can see there's a black inner portion of the rusticles that you don't see in these other images. So that was really informative, especially this difference between black and orange iron oxides, because these black iron oxides may be semiconductive. For example, this is what I, after doing all this analysis and looking at that picture, envisioned that the rusticles are inside. So this is just like a slice of the rusticles, and it has the inner cavity that, as I was telling you, is acidic inside. There have been reports of rusticles having pH 3s inside the cavities. So the inner layer of iron oxides is magnetite or magemite, that they are semiconductive, and they are forming a galvanic couple with the steel of the shipwreck. And once they come in contact with the seawater, like they start dissolving the iron in this little cavity. And once this iron starts leaching out of the cavity, it comes in contact with the seawater and the small amount of oxygen that it has, and precipitates. And that's what's giving the rusticles the vertical growth that we saw in the last images. So this is my idea of a rusticle, and how it influences the corrosion process is precisely with this contact between the semiconductive iron oxides and the seawater at the tip. So this is just dissolved iron or iron chloride that leaches out, and once it reaches the oxygen, it precipitates. And then we'll see that they reach certain length or weight and they fall off. So we know that the rusticles were mainly iron oxides, but what else was in the rusticles or around the rusticles in the seawater? We had the seawater samples analyzed, and we found that the seawater samples in near the bow of the Sydney, they had really high concentrations of zinc. And it was above the toxicity levels for these metal or metalloid. So we were also wondering, is this being reflected also in the rustical chemistry? Yes. Here you can see that the Sydney has much more zinc in the rusticles than the Kormoran. But then after this, yes, zinc is toxic, but what other toxic things can be present in the rusticles? We didn't have any more seawater samples to analyze, so we had to continue with the rusticle samples, and we found that yes, they are really, really toxic. They have really high amounts of arsenic, mercury, copper, and lead, but the Kormoran had less concentrations of them than the Sydney. And that may be related to what Andrew was saying, that there was more like life and anemones in the Kormoran than in the Sydney. The Sydney is just a really toxic environment, and these are all above their toxicity thresholds. So why is there such a significant difference between the Kormoran and the Sydney? They are two very different ships. Here you can see the Kormoran with the previous name when it was a merchant ship, as Laura was saying, and here you can see the Sydney, a full-on warship. So that's the difference. The Sydney was conceived as a warship, therefore it had high-strength steel. It has a very well-maintained zinc oxide paint, and regular changes of the camouflage, regular like pulling out the whole ship and putting in a dry dock and clean the whole hull. And the Kormoran was a merchant ship converted into a warship. It was built with soft shipbuilding steel that wasn't designed to like hold the impact of torpedoes. It had lead iron oxide paint, very poorly maintained, because the purpose of the Kormoran, it was a raider, so it was just go around the ocean, sink as much as it can, and it had no time to go into a dry dock. The captain was also complaining on the amount of biofouling the lower portion of the hull, the underwater portion, was experiencing, that it was slowing them down, and that they had to every once in a while careen the boat and scrape all the green muck that was present in the hull, and that was slowing them down. But they couldn't ever go into a dry dock. I don't know how they did it, but they managed to lift a little bit of the boat, scrape, and then go lift on the other side of the ship. So it was a really, really good information, because then we can see what happens with the above and underwater portions of the hull after they sunk and spent 70 years in the bottom of the ocean. So another chemical analysis that we did to the rusticles was the amount of silica, because it's usually the second most abundant component in the rusticles after iron oxides. So this data just gave me the idea to Google iron and silica, and these appeared. Chemical gardens that, for me, they resemble like rusticles, just that they are growing from the bottom up, not hanging like proper rusticles. So I kept researching about these phenomena, and it's an iron chloride crystal that is immersed in a concentration solution of iron silicate. So now what I've been telling you about the deep sea conditions, the chemistry of deep sea, you now know that the silicate increases and all these anionic compounds increase with depth, and the corrosion process can provide a concentrated iron chloride solution that, as I was telling you, leaches out of the rusticles and can start forming these deep sea chemical gardens, as I now call them. So besides the plant-like structure of these chemical gardens, you can see there are like algae growing and floating towards the surface. They can also explain these little microstructures that we used to think that they were bacteria. In fact, they are really similar to Zeta proteobacteria here. Where is it? these little tubes, and that Laura was presenting in her images, they resemble Proteobacteria, but you can see other type of structures. You can see pom-poms, you can see spherical structures, and they are mostly composed of iron and oxide. And we could also see a difference between the microstructures in the Sydney and the Kormoran. The Kormoran had more of these tube-like structures, and the Sydney had more cigar-like iron oxides with some cavities, but they are really, really complex. You can see that they are a lot of specific surface area. These iron oxides, goethite, lepidocrosite, they can have very high specific surface areas of up to about 195 meters squares per gram. So this gives the rusticles an extremely large surface area for complexation, adsorption, and electron transfer. So this is why the whole the coating is leaching these compounds into the water, but then it's getting back into the rusticles, and the rusticles are kind of remediating the site at the same time the hulls are polluting it. So this will also increase the availability of a corrosion process, and they are beautiful. And you can see this one specifically gave me another idea that, well, it just reinforced the idea that it was a chemical process. If you can see, it's full of spikes inside. And if there was a bacteria living in this, it would be like the bacteria would be living in an iron maiden poking inside the membrane. So this was just a reinforcement of the idea that I had, that it was mainly a chemical chemical process, and that the bacteria are playing another role. That is another part of my PhD that I'm working on to establish what are the roles, or the role of the bacteria. So here is what I was mentioning about the above water and underwater portions of the hulls. You can see that the above water portions are basically rusticle free, and the underwater portions of the hull, you can see, for example, in the HMAS Sydney to the left, that the rusticles are very localized, and in the Kormoran it's just a sheet of corrosion. And we were also thinking that it may have something to do with the biofouling present in the underwater portions of the hull. But these biofouling, it would mean food for deep water communities. And this is another characteristic of deep sea environments, that all the food comes from above. So when it starts sedimenting up to the bottom, the food becomes really scarce, and the only thing left is very recalcitrant organic matter. So when the ships just sunk, all this food was consumed like in a really short period of time. So another possibility was that since it was an underwater portion of the hull, the coating was soaked in water. And once they sunk, they reached this extremely high pressure all of a sudden, and these little pores were filled with water, but haven't reached enough, like the metal part underneath the coating. So when it reached this high pressure, the water was pushed up to the metal, and then it started the corrosion process. And this corrosion process then started bleeding the corrosion products onto the surface. And that is what we now see as the rusticles developing in the underwater portion of the hull. We still don't know why the above water coating is almost intact after 70 years of being under the same deep sea conditions. So if you have any ideas, please. So this is my rustical formation hypothesis. It needs a coating or surface defect for where the localized corrosion process starts. It forms a crevice. All these localized corrosion start leaching these iron chloride, and it deposits at the mouth of this crevice or this little cavity, and then it develops this rusticle. with a gradient of iron chloride inside and keeping the rusticle, let's say, alive and growing. How much iron do we need to create a natural rusticle? For example, the ones in the Titanic that are massive. For example, a 1 meter rusticle with a 21 centimeters in diameter, 1 kilogram of mass, and 12 liters of volume. We only need 550 grams. The other things are oxygen for the oxides and how porous they are. So they are just fluffy, as you could see in the pictures when the ROVs passed next to them and they just poof. So the hull of the Sydney had a total steel thickness. Also looking at the Sydney plans and the twin vessel that was created with the Sydney, it had an armor of 11 centimeters thick, and the whole area that we need is around 5.3 centimeters squared to create a rusticle of 1 meter. So yeah, I presented this research on a chemobryonics conference. Chemobryonics is the study of biomimetic chemical structures. So this is, it's basically chemical gardens and all their different uses and applications of these chemical gardens. We got really nice feedback, and this ongoing work is the rusticle microbiome analysis and to determine what is the role of the bacteria in the rusticle's iron oxide composition and in the corrosion process. So thank you very much, and questions and comments.